But you can't do it the other way. If you have a region where one of the variables is stuck between two constants, the other one's between two functions, you can only go this way and keeping yourself between these two functions. If you try and go this way, you're going to punch out of the curve. Does that help a little bit? Okay. All right, can I say we're done with that problem? Okay, I will just say it then. We're done with that problem. Yeah, it is pretty crazy. All right, we are now going to move away from surface integrals, and we're going to finally get to a topic called flux. But to get to flux, we have to build up some stuff first. So the first idea here is this idea of what's called an oriented surface. So an oriented surface is a two-sided surface, and I put here there are such things as one-sided surfaces. Have you all seen a one-sided surface before? Mobius strip. Klein bottle is a three-dimensional Mobius strip. So Klein bottle is an example of a solid with no volume, a volumeless container. That's a Klein bottle. Okay, Mobius strip. Where's my sacrificial piece of paper? That looks like it has stuff on it. I'll just tear the bottom of this off. If you've never seen a Mobius strip, this is a surface. We would consider this a surface with two sides, without arguing about the edges being sides, right? So this is, most of us would consider to be two-sided surface. My index finger and thumb would be on the two separate sides, right? Side one, side two. But if you take this strip of paper and you twist it one time and fold it upon itself like this, you get what's called a Mobius strip. It's a little better if I make it longer and more narrow, but this is called a Mobius strip. And you could argue that it's still two-sided, but it's not. It's only one side. And the way you can prove it is you just start at my thumb and you just go around. And as I go around, I'm going to wind up on the side that my index finger is on. And then I keep going and I wind up back on the same, I'm still on the same side my thumb is on. So this is an example of a one-sided surface, Mobius strip. Now, the Klein bottle, see what I did here? I took these two edges. I'm going to start going into topology here, I'm sorry. So here was my strip of paper. And what I did was I took these corners, and let's call this A, B, C, and D. Well, I'm going off. What would happen if I took and I put A on top of C and B on top of D? I would go like this, right? And this would still be a two-sided surface, right? But if I take A and take it to D and B and take it to C, then what I'm doing is I'm twisting it and I'm putting it like this, right? Okay? So that right there is your Mobius strip. Understand? So what if I do this? What if I take A to D and B to C, right? But at the same time so I'm going to twist this and put it together, okay? But at the same time, I want to take this whole edge and paste it to this edge here. So it's kind of like I want to wrap this edge around, but at the same time do that twist and paste, and that's how you get a Klein bottle. And it like punches into itself, and the inside is the outside. Look it up. You cannot represent, a Klein bottle is impossible to create in three-dimensional space. We have representations for it, but it's not truly, you need 4 dimensions to actually have a Klein bottle. But okay, I'm way off topic here. I should just take this out. I should just take that out of the notes completely. All right, an oriented surface is a two-sided surface in which the normal vector at every point on the surface exists. So remember, a normal vector is a vector that is orthogonal to the surface, just like a normal vector on a plane. So if we have a surface, and at every point you have some normal vector. and such that the normal vector varies continuously over the surface. So again, my little analogy here. I have a surface, I've got different normal vectors, and as I move around, those normal vectors change, but they change nice and continuously. Like it doesn't do this and all of a sudden the normal vector flips over and it's the other way. So it's a continuous, nice continuous changing of the normal vector. So if you have that, you have what's called an oriented surface. Now there are two possible orientations for this surface. You can have what's called positive orientation, which would be where your normals point in some direction. And then you would have what's called the negative orientation, which would be that they point the other way. So it's like you got the surface, you've got a normal vector. You could say that's the positive orientation, and that would mean that the normals pointing inside are the negative orientation. Understand? Yes? Pretty straightforward? All right. With these surfaces, we can choose two possible orientations. It's our choice. All right, so how do we actually compute the normal vectors of an oriented surface? How do we figure out those normal vectors? Well, doesn't the partials cross product give us a vector that is orthogonal to our surface? And what would happen if we divide it by its own length? It would be a normal vector. It would have a unit length. The length of that vector would be 1, right? So that's how we can compute a normal vector given a surface that we can draw. Now we can draw them with r of uv. If we can draw it, then we can always compute the normal vector using that formula. Now if we flip it over, we just change this, whatever we get, we just change the side, and that'll give us the other one, right? Pointed the other direction. Now, in the special case that our surface, this keeps coming up, right? This special case. In the special case where z can be expressed as a function of x and y, then this computation becomes this. And that's just the shortcut formula. Here's your cross product, and here's the magnitude of the cross product. That should look familiar because that's what we were using in the integrals a little while ago.
Is the same case for x and y?
And then, yeah, you mean if x is a function of y and z? Yes, but these change a little bit, so you have to be careful with this.
Will your 1 just replace that? Like if x is equal to the function yz,
Mm-hmm.
1 be replaced in the x position?
This? Oh, yes, this would change, yes. I would encourage you to work through them because really I kind of showed you where this came from last class, so you could go back and recreate it yourself. All right. Now, an oriented surface is any surface where we can compute normals, and those normals can point in one of two directions. A closed oriented surface is a surface that is closed, like a sphere. That means that it encloses a solid. So it creates some solid by closing. So it's not like this nice little sheet that just continues forever. It has to come back around and close on itself. So it's kind of like when we were doing curves, right? C. But when we had the curve come back and close, then we had a closed loop. Now, a closed oriented surface is a surface that closes it all up, right? So we have a solid. And guess what? 13.9, divergence theorem, we're going to be able to calculate things over the solid it encloses by using a triple integral. That's what the divergence theorem is at the very end. It says you want to do this really complicated thing on this crazy surface, just do this triple integral. All right. All right, so if we have a closed surface, then positive orientation is the one in which the normals point away from the solid. So we all just agree that that's what positive orientation means. So when we have just a random sheet of paper floating around here like this, and I tell you that's a normal vector, you could argue with me that, no, this is the normal and that's the negative. Like this is the positive orientation, that's the negative. We could argue back and forth all day because it's really up to you and me to determine what we want to call positive and negative. But once you close the surface up, like a sphere, now there's no arguing. Positive orientation goes out, away from the solid, and negative orientation goes into the solid. All right? And we don't discuss it. It's just understood. That's the way it is. All right. Flux. So now what we're going to do are surface integrals, but our surface is now within a vector field. So we're going to take that surface we had earlier and throw it into a vector field. And we've got lots of notation here. The first thing is, given a vector field F on an oriented surface, so not closed, just oriented surface, with oriented surface S, with unit normal vector N, and the vector equation of the surface, R of UV with U and UV and D. If we have all this stuff going on, vector function, right? Not scalar function, vector function. We've got a normal vector to our surface. This is what we use to draw the surface. Then this double integral right here, this is brand new notation. Do you see the difference between that notation and the one before? The ds vector S, not capital S vector. That's what distinguishes this from the previous one. And also, this is F, it's not scalar function times, right? It's the vector field dotted with this. Now, what does this mean? Well, here's what it means. We're going to take the vector field and dot it with NDS. Oh, whoa, what just happened? What's ds capital S without the vector on top of it? That was surface area, right? So isn't this really saying normal vector times, what was that surface area? Magnitude R U cross R V dA. Isn't that what that is? Right? Like this? Yes? Okay. And by the way, is this dot or multiplication here? Multiplication, because this is all a number, isn't it? So this is scalar multiplication there. I'm going to explain what this all means, but I just want us to understand the formula first. Then this formula becomes this formula. What the heck? Where did that n go, and where did the absolute value go? And
Don't they just go away because n is, your normal is going to be your vector over.
well, this didn't go away because this is not the same as this. Right? Look, this is magnitude of the cross product here, and this is not the magnitude. So all you'd have to do here is mess around with some of your identities, like, well, just do it this way. What is the normal vector by definition?
That's your cross product over your magnitude of.
That's the cross product of the r's over the magnitude of the r's, which would cancel this out, right?
That's what I was trying to say.
Yeah, okay, I didn't hear you saying that. I thought you were saying that this was going to be 1 or something.
No.
Okay. So just a second ago, I told you what that was, right? And if you cancel out this with the one on the bottom, you'd get this. Okay. So in order to do this flux, what we have to do, we have two options, okay? And we will use both options. I want you to look at this as two different formulas for it. We can either take our vector field and dot it with the normal vector, figure out what that is, and then just do a regular old surface integral, like we did in the previous problems. Or what we can do is take our vector field and dot it with the cross product of the partials, figure out what that is, and then do it like a double integral over the region D. Our choice, every problem is going to dictate how we do it. Now you probably want to know what the heck it means, right? Like, what does this integral represent? Because it's flux, and we use this in physics. So here's the way I can try and help you see what's going on. Okay, we have, we're going to do a good old sphere just to make it something we've seen. So we got this surface, right? And we've got this, there we go. So I'm going to move my point. I'm going to try and get it over here to that little patch so we can talk about what's going on in this patch. Let's move down here. Come on. It's not doing what I want. Get there. The vector's very boring there. I need to move it. I guess I'm not going to be able to use that patch. I'll just use that. Okay. So what we have here, imagine that you're on this surface, right? There you are. Now, within this space, you have a vector field. So at every point, there's some sort of vector. Yes? And we can't show it because it would just fill the space up. Imagine that that is, again, like some sort of force that's pulling you in that direction. Yes? So if I am on this, if I'm on this point, the green vector right here is our vector field. Okay? It's wanting to pull me this way. The black vector is my RU cross RV, which is that vector that's what? Like orthogonal to the flat tangent plane that's there? Yes? And then the red vector is what? Can you tell what the red vector is? It's the what? Projection of the green vector onto the black vector. Right? If I take the green vector and project it onto the black, I get this little red vector. And what that's telling me is the component of flow or pull or gravitation, whatever you want it to be. It's giving me kind of like in the direction directly out of the surface, in the direction of the normal. What's my pull in that direction? Understand? It's like you're taking, if you take a vector on a flat sheet of paper, then we have like an x component and a y component of the vector. This is kind of getting this vector and it's taking and transforming it into a vector that is in one direction. It's saying in that direction, how much pull do I have? The direction directly away from the surface. Understand? Okay. If we do this projection of F onto that and do all that, we actually get F dot N ds. That's what the formula will become. This is the projection formula. And so all this does is creates this measurement of how much is going out at that point. And then the integral will add it all up. So you get something like this. Now I'm going to go to that patch. So imagine I take an infinitesimal little patch, a little ds, a little tiny infinitesimal patch, and I create a bunch of normal vectors. So those are my vectors that are pointing out. Those are my black vectors. Okay? And then I look at the vector field at all those points. Then I project them, and I get all those red vectors. And let me take all those other ones out now. Those are your projection vectors. And then imagine doing it for every point in that little patch. And you get this infinite number of vectors that are coming out of this. And what that's giving you is it's giving you a flow out of that patch. All right, so if this is an electromagnetic field, it's giving you a measurement of how much flow, electronic flow, is out of that patch. And they call that flux. All right, but water is always easier to visualize. So imagine you've got water trying to flow out of this little patch. This is measuring the amount of flow through that patch. And then what you're going to do is you're going to add up all that flow on the entire surface. That's what your surface integral will give you. Does that kind of make sense? Okay. Another thing that I've heard used is like if you have a river flowing and you put a net there, the water will still flow through the net, but you're somehow trying to measure the flow through that net. So your net is like this little patch. That's your little net, and you're measuring how much is flowing through that patch at one time. Understand? Okay. Let's get down to calculating flux then. Remember the two formulas. Find the flux of the vector field f of x, y, z equals y, comma, z, comma, x across the unit sphere. So good old unit sphere again. This is what we want, right? That's our new formula for flux. And that has two equivalent representations. We can do double integral over S of f dot what? Normal vector d capital S. Or if we'd like, we can do double integral over, okay, f dot r u cross r v, but what? d a, and d over here is d. Remember, d are the restrictions on u and v. S is your surface that is drawn by u by r of u v. So let's see, which one do we want to use here? Can we do the last one? What is our r of uv? Do we know our r of uv? Do we know what draws our surface? Because this is the unit sphere. We do, right? We've done this three times now, at least. Okay, so what's r of uv? Let's stick with the same one that we've had. What is it? I don't remember, I'm sorry. Because I always switch it up and I don't want to mess it up. It was, yeah, it's unit sphere, so we can use one. What were we using u and v though?
Sine u, cosine v.
Okay, sine u. All right, cosine v.
Sine u, sine v. Cosine v.
Yeah, I've got, all I need is that first one. And once I have the first one, then I'm okay. All right, u is between, we want the whole thing, right? U is between 0 and pi. V is between 0 and 2 pi. Okay. I need to take the cross product, which we've done before. All right, let's hold off on that, because I know we can get it, but what does this piece right here mean? What does f by itself there mean? Because it means something, but it doesn't, it's not just f. You need to understand in this notation that this actually means f of r of u v. That's what this means. That means you're going to take your vector field and evaluate it along your surface. So it's a little bit deceiving that f is just sitting there. You could replace it with what? This vector, y, z, x. But what's y, what's z, what's x? Well, this is y, and that's z, and that's x. You see? So you're going to wind up plugging this surface into that vector field. And that's what this means. You want to go ahead and get what this is right now? What would that be? What's that vector? Sine u, sine v, because that's y.
Cosine u.
And then z, cosine u. And then x, which is sine u, cosine v. Okay, so there's your f. I need the cross product. Now, that is on some other page. Cross product of the partials. So who has that readily available for me? Not no magnitude, though. Sorry. It's ugly. I remember that. Okay, sine squared u cosine v. Are we in the next component now?
Yes.
Sine squared what?
U, sine v.
Sine v.
Sine, not sure if it's v, then cosine u.
I thought they were both the same.
Yeah, I think it's sine u. Cosine u.
Sine u, cosine u. Everyone check in their notes. We should have at some point did RU, partial of r with respect to u cross partial of r with respect to v and got this. Do y'all see that? Yes? All right, so I'm supposed to now do what? Dot these two vectors together. Any questions? 'Cause I'm going to erase some stuff here. Didn't show a lot of work, but okay, let's do this. We're going to do double integral. I'm continuing up there. We're going to do our double integral, and let's go ahead and put what our limits of integration are, because everything's in terms of u and v. So I can go 0, 2 pi, 0 pi. And then I'm going to dot. Here we go. This vector dotted with this vector. Dot products are the easy ones, right? So what do you get when you do this and that? Sine squared u. Sine cubed u. Sorry, I didn't hear that. And then sine v cosine v. Plus, because it's a dot product, right? Plus what? Sine squared u. Sine v cosine v. Oh, cosine u. Thank you, thank you, thank you. So that times that. And then finally, this and this. So sine squared u, cosine u, cosine v. D u d v. You could break this all up. I'm wondering if there are any identities. Boy, I sure hope this cross product was right. Pardon me?
For the most part, it should be okay, because a lot of them are constants.
Yeah, I was hoping we'd get some identities in here or something. Like a Pythagorean identity or something, but I don't see it. Well, guess you just have to take that the rest of the way, huh? Yeah, let me do something real quick. How are we doing on time? 28. Why is this not connecting? I'm actually looking at a lecture from the past. Yeah, this is it right here. So what I'm going to do is I'm going to open this up. I'm going to see if I take this any further. I'm almost there. Let's see if it matches. All right. Just ignore that idiot right there. Okay, sine squared cosine v, and then
Is that a V or U?
where?
Oh, no, it's cosine U. Okay.
This looks like the same thing, doesn't it? Okay, so that's okay. Let me see if I took this any further. Doesn't look like it. I didn't do it. Okay. So I want to keep it consistent, so we'll just leave it at this. But, I mean, you can at least appreciate what it would take, right? I mean, it's not that it's difficult. You could do like this one, right? You could split this into two integrals and multiply them together, right? This one right here, you could peel off one sign and then turn sine squared into 1 minus cosine squared and then do basic u sub. So that is a doable problem. This one, split it into two integrals and multiply them. The u stuff, sine squared u, cosine u, that's a basic u sub. And then, of course, the antiderivative of sine is pretty easy. And then this one right here, same thing, basic u sub. I mean, it's all doable. Do you agree that's doable? All right. All right, there is a typo in the notes. If you happen to print these off, there is a typo in the notes. So I want to make sure you correct the typo. I have not corrected it online. I always correct it once I get here to this section. Well, I've got some good news. The flux integral has an easier computation in those special cases, again. So if your z is a function of x and y, your surface is a function of x and y, and your vector field is written in that form PQR. We've done this in the past, right? Broke it up PQR. Then the flux integral is f dotted with this thing, but you don't need to worry about any of that anymore because this is what it becomes. It is the double integral over d of negative p, so that means whatever this is, times the partial g with respect to x, minus q, which means whatever this is, times partial of g with respect to y plus r, all of that dA. So you don't have to do any magnitudes of you don't have to do any cross products or anything like that. Very nice and very clean. The important thing on this is this right here. This formula works as long as we are talking about a surface that is got its normal vectors pointing up. So remember I said surface, this is a surface, this is a function of x and y, and the normals could be this way or this way, right? This way or this way. If it's not closed, then it's your choice. This formula works if you are saying the normal points up. If the normal is going to point down, then you're going to change this to plus, plus, minus. Understand? Okay. Now, with that same idea, and I think I'm coming up to the point that I had the typo. Does anyone have the notes with them by chance? I'm glad I provide those. Okay. In the special case where x is a function of y and z, so now our surface is which way? Like this, right? Like this. Then here's the formula. Again, PQR, here's what you have to compute. P minus Q partial g with respect to y minus r partial g with respect to z. So long as the normal vector you're talking about is pointing out towards you, like this. If you do it on your normal vectors on this side, then you're going to have to change these to minus, plus, plus. Okay? And then I believe this one for sure is the one that had the typo. This one right here. If y is a function of x and z, so now if your surface is like this, okay, then and your normals are pointing out the right side of the y-axis, which means this way, then your formula is this one right here. I don't expect you to memorize those. Just know they exist.
Is that one of them on the paper?
What's that?
Is that one of them on the paper?
Is one of them on the paper?
Like the format sheet you gave us.
Let's see. Let's go back to the chapter summary here. I gave you one of them. If z is a function of x and y. Five minutes. I think we can set this one up. So you have a surface here. Find the flux of the vector field. F of x, y, z is x, y, y, z, z, x across the surface S, where S is part of the paraboloid z equals 4 minus x squared minus y squared that lies above the region x is between 0 and 1, and y is between 0 and 1. Use upward orientation, meaning normal vectors pointing upward. So we have a paraboloid. There it is. Okay. That paraboloid, the part of that paraboloid is a function of, our surface is a function of x and y, right? So we know that z is some function of x and y. We have a vector field, in this case, P, Q, and R, right? We have restrictions, right, which is going to make up our domain right there. And so according to the previous section, or the previous note, we are looking at this one right here. We have a function of x and y. Our normals are pointing upward out the z-axis like this. So we need to compute double integral over d of negative p partial g with respect to x minus q partial of g with respect to y plus r dA. So what would this double integral be? Let's see if we can't write it down. Please don't talk over each other. It's very rude. You know, raise your hand. I'll call on you. Anybody? What's your domain? Those two things, right? 0, 1, 0, 1, right? All right, so we're going to go from 0 to 1, 0 to 1. All right, what is negative p? Negative xy. What's the partial g with respect to x? Negative 2x. So I'm going to do negative p, which is negative xy, times partial of g with respect to x, which you just said was negative 2x, right? Like that. Y'all good with that? Sure? Minus q. What's q? So minus q, which is yz, partial of g with respect to y. Negative 2y. Okay. Plus r. Plus zx. And then what? dy dx. Yeah, that doesn't matter, right? Because they're both from 0 to 1. All right, this is just a good old-fashioned double integral, except one little issue. What's our little issue that we have? The z. The z. We have variables x and y, but then we've got a z in there. But, yeah, exactly. What's z? Z is 4 minus x squared minus y squared. So I'm going to replace that z and that z with 4 minus x squared minus y squared. And then I will have a rather ugly looking double integral, but a double integral nonetheless. And it'll be a great point for us to stop and let you go play with it instead of me. All right, this will be positive 2x squared y. And then here, positive 2y squared. So I'm just putting things together here. Positive 2y squared, and then z I'm going to replace with 4 minus x squared minus y squared. And then this one right here, plus x times 4 minus x squared minus y squared. dy dx. Then you could just expand it all out and do your integration. Right? All right. Have a wonderful weekend. We're going to finish up 13.7 next class. And then we get Stokes' theorem and then divergence theorem. It's going to be great. Let me go turn off my camera first. Yeah. Did I ever turn it on? Yeah, I did turn it on.